session. Myself, I am Shravani, Assistant Professor from the Department of CSC. Today we are having the last topic from your third unit, which is randomly built binary search trees. And till now you have seen what is meant by greedy method, and also we have seen there are several number of applications involved with your greedy method, like job sequencing with deadlines and knapsack problem, right. Likewise we have seen number of applications, right. So after that you are coming with probability and randomized algorithms. So under that you have seen hiring problem, and also you have seen randomized quicksort, and this is one more which uses randomization concept, and that is randomly built binary search trees. Now we will see in detail. So basically in today's lecture I am going to cover what is meant by randomly built binary search trees, followed by algorithm to build this rbbst. Along with that we will see the analysis part and coming to the objective. So with today's lecture the students can able to understand the concept of randomly built binary search trees in detail and outcome. After learning this particular lecture, the students are able to build the randomized built binary search trees for the given tree. The tree is a binary search tree. What is this randomly built binary search tree? So it is a BST formed by, BST stands for binary search tree, formed by inserting the n number of items into the binary tree in random order and maintaining the binary search tree variance. That is, here it is obeying the binary search tree rules, and it will insert the elements into the tree, which is a binary search tree, but it will insert the elements in a randomized order, that is in random manner, but not in a given fashion. Now the random order means we need to compute the random permutation of n items. We need to compute the random permutation of n items, and we have to insert them one after another into the tree. So now why we have to go with random permutation? That is, for suppose let us consider I am having a binary search tree and where I am having elements in the descending order. Let us consider in the descending order, that is 80, okay, 80, 70, 60 and 10. So now how to draw this? 80 followed by 70 followed by 60 followed by 10. So this is strictly binary search tree, and whose height is 1, 2, 3, which is 3, right. So now if I am going with a randomized permutation, that is I'll reorder them by using any randomizer function. So then maybe I am getting a list like this: 60, 70, 80 and 10. Let us consider this is my list now. So now 60 I will insert first, and then 70 and then 80 and then 10. So now what is the resultant height? The resultant height is now reduced to 2. Previously it is 3, now it is reduced to 2, right. So somehow we have reduced our height. So basically if I have reduced the height means automatically it is reducing the time also. The time required will also be reduced to construct that particular tree. So that's why we are using a randomizer function. So now they are used to perform randomized binary search tree sorting. So here after getting this randomized binary search tree, what we are going to do is we are going to find out the in-order tree traversal. That in-order tree traversal is nothing but your sorted list. So here by taking a randomizer function, you are finding the randomized binary search tree. So after constructing this randomized binary search tree, you are going to find out the in-order tree traversal to find the sorted list for the given list of elements. So now, what is the algorithm behind this randomized binary search tree algorithm? So basically it takes the elements from 1 to n, that is why the array consisting of a of 1 to n. Now initially we need to apply the random permutation on a. And next apply BST underscore sort, which is nothing but apply sorting on the resultant binary search tree. Okay, after making the permutation, random permutation, we need to construct the BST, right? So on that BST I have to find out that sorting, nothing but I need to find out the in-order traversal. So now what is a BST sort algorithm? This is the BST sort algorithm. So basically BST sort algorithm here, it takes A is nothing but n number of elements, all the n elements which are going to be inserted into your tree, right? That is your input, and here initially we have to build the binary search tree, followed by I need to find out the in-order tree traversal. That in-order tree traversal is nothing but your final sorted list. That's why we are finding this. So basically here ran BST sort. This is the algorithm for randomly built binary search trees algorithm. Here it takes all the n elements, and here I am applying the random permutation by using any randomizer function that depends upon the language which we are using, and now I am applying the BST sort. So now coming to this BST sort, this is the algorithm for this. So here initially this BST sort takes the n elements, and here I need to construct the binary search trees first step, and after construction I need to find out this in-order tree traversal. That is our sorted list. So now let's see randomized binary search tree. Okay, how to apply this sorting. Now the time complexity of randomized quicksort, which you have seen previously, what is the value? Big O of n log n, right? So now randomized quicksort, whatever the time complexity it is requiring for randomized quicksort, the same complexity is required even for this randomly built binary search trees. So I am calling in short it as rbbst. Okay, so now that is E stands for runtime. Okay, E is the expected runtime of RBST sort is equal to expected runtime of randomized quicksort. So now finally, so that implies here runtime of RBST sort I can represent with the help of height. So here E is the expectation, summation x belongs to t, depth of x. So here runtime of RBST sort I am explaining with the help of depth. So depth of x is equal to big O of n log n, as you have already previously seen what is the runtime of your randomized quicksort. So now if I am taking this n to this side, what happens here? N log n, right? So here it will be 1 by n. So E of 1 by n into summation x by t, depth of x is equal to big O of log n. So now average depth, so here 1 by n summation of depth of x, what it mean? Here x1 plus x2 plus x3 plus so on xn by n. So here this can be written as x1 plus x2 plus so on plus xn by n. So this is nothing but average, right? So average depth of a randomly built binary search tree is equal to big O of log n. Is equal to big O of log n. So now objective, what is our final objective in this particular topic is expected height of randomized built binary search tree is equal to big O of log n. So here with this analysis we have seen that the average depth of RBST is equal to big O of log n, whereas now we are going to prove the average, okay, not the average, here the height of randomized binary search tree should be equal to big O of log n. That we are going to prove in this lecture. Let's see an example here. So here I am having a strictly binary search tree which is in the increasing order. So which is inserted in the increasing order and which is having the values 9 from 1 to 9. Height is equal to how much? 8. That is 1, 2, 3. So now 8. And how many number of values are there? Number of values are 9. So here for 9 values I am having the height as 8, right? So when I am constructing the BST, here this is also satisfying the BST invariance or BST rules, right? So this is a BST, but whose height is 8 and the values, the number of values are 9, right? So now I am going to construct this BST into, I am going to change or convert this BST into randomized binary search tree. So how? We will see now. So BST, after applying randomized permutation, okay, here how to apply randomized permutation. So in Python I have numpy, right? So np.random.shuffle. So for suppose if I am using a Python language, so there I have used one randomizer called np.random.shuffle. So if I am applied that, so I will be having like different number of combinations. So here I am showing you 4 combinations out of that. So the first combination is 63415978. So if I am going with this sequence and if I am inserting each and every value in the order, I will be having the first BST as like this. So this is the first BST. That is a randomized BST, and this is the second BST, and this is third one, and this is fourth one. And for this, the sequence is 69514723, and for this 941287, for this 826154. So likewise, I am having different sequences for each and every given sequence. For example, here I am having 9 elements. So 9 factorial ways. Okay, there are 9 factorial ways. So 9 factorial permutations. So those many number of sequences I can have, right? So out of 9 factorial, I am showing you only 4. So if I am taking this 4 combinations, what happens here? What is the height now? 1, 2, 3. So here the height is 3, and here the height is 1, 2, 3, 4, 5. So here the height is 5, and here 1, 2, 3, 4, and here 1, 2, 3, 4, 5. So finally, here for the given one, it is 8. Now, if I am taking a randomizer, okay, if I am taking a randomizer or if I am applying a random permutation, now what happens? The height is somewhat reduced to 3, 4, 5. So, somehow we have reduced the time also, right? So, this is how we are going to construct the randomized binary search trees. So, now height of all the trees, if you have seen here, the height of all the trees are less than 8, whereas for the previous one, which is a given BST, which is 8. And there is one more thing, number of binary search trees created for n number of items is equal to 1 by n plus 1 into 2n Cn. Here 1 by n plus 1 into 2n Cn. For example, here in the given n is equal to 9. So 1 by 10 into 2 into 9, which is 18 C9. So these many number of trees I can have, those many number of, not only trees, those many number of binary search trees I can have for the given 9 elements. So now let's see the analysis. So before going to the analysis, we'll have outlier of analysis. Outlier is nothing but what are all the different theorems or what are all different definitions we are using for our analysis part. So the first one is Jensen's inequality. Mathematically, okay, when you are going for mathematics, you will have a detailed explanation over there. Here I am giving you the explanation only regarding my concept, which is relevant to my concept. So Jensen's inequality says that f of e of x is less than or equal to e of f of x. That is where f is a convex function and x is a random variable. So here f of e of x, e is nothing but expected, okay, expected or estimated value. So f of e of x is less than or equal to e of f of x, where f is a convex function, and in detail we will see what is meant by convex function in the next slide, and x is a random variable. There is one more thing, exponential height of a randomly built binary search tree. Exponential height is yn is equal to 2 to the power of xn. So depending upon the depending upon the values, here our height will be determined. So now where xn is the height of rbbst, here yn is the exponential height, exponential, whereas xn is the normal height. Please remember. Now prove that. Here we are going to prove in our analysis part, we are going to prove that 2 to the power of e of xn is less than or equal to e to the power of 2 to the power of xn. Then I can say that e of yn is equal to big O of n cube. So if I am proving either of this, okay, then by using this one, if I am substituting this in this, what happens is, so here by using substitution method, that can be evaluated to big O of log n. So finally I want to showcase this with the help of this lemma. So here we are going to prove that 2 to the power of e of xn is less than or equal to e of 2 to the power of xn. So, which implies which is equal to big O of n cube. So, this is all done by mathematical induction. Now, hence we can say that e of xn is equal to big O of log n. So, that big O of log n we are going to prove with our analysis part. So, for doing that, you need to remember all these formulas. Let's have what is meant by convex function. So, now f, okay, there is a function f, r to r is a convex function if for all alpha comma beta is greater than or equal to 0 and alpha plus beta is equal to 1 if we have f of alpha x plus beta y is less than or equal to alpha into f of x plus beta into f of y. That is nothing but here f of alpha x plus beta y is less than or equal to alpha into f of x plus beta into f of y. So, this is the okay. So, now if alpha plus beta is equal to 1 and beta is greater than or equal to 0. So, this is the this will be, this inequality is equal. Now, we can say that f is, if this is equal, then we can say that the given f is a convex function. Now, for Jensen's equality, your f should be convex function. Now, what is your Jensen's inequality says that f of e of x is less than or equal to e of f of x. Your f of e of x is less than, we will prove that. So, in order to prove this, we are using some lemma. So, before going to that, here is a small graph. Here is a graph where I am having this point as x and y, and here this is, okay, this is a curve, and here this point, okay, is f of alpha x plus beta y. And if I am drawing a straight line, this is a curve, right? If I am drawing a straight line, so here straight line will be, generally what is a straight line here, ax plus by is equal to 0, right? If it is passing through a origin. So, here I am having a coordinates like with alpha comma beta, right? So, here this straight line I am representing with alpha into f of x plus beta into f of y, whereas this intersecting one is nothing but alpha x plus beta y, right? So, now by using all that, here we are going to prove this f of e of x is less than or equal to e of f of x with this following lemmas. So, here to prove this, we are using the following lemma. So, here f is a convex function and alpha 1, alpha 2 and so on alpha n, these are the values. So, if I am having like this, so summation I is equal to 1 to n, alpha I is equal to 1. So, here there are number of random values from x1 to xn. So, here we can say that from this f of summation I is equal to 1 to n, alpha I xi, that is nothing but here the point alpha I xi is less than or equal to summation I is equal to 1 to n alpha I f of xi. Nothing but here this alpha I is taken before and f function we are applying to your x, which is a random variable. Now, which implies f of e of x is equal to e of f of x, where e of x is the expectation. So, let xn be the height of, here we are going to find out your height of rbbst. So, xn is the height of rbbst with n elements, and let k be the rank of root. So, here if this is your root node and this is your tree, left subtree and right subtree, and if k is a rank of root node, then k minus 1 will be the rank of this tree and n minus k will be the rank of this tree. That is nothing but here k minus 1 is the rank of this left subtree and n minus k is the rank of right subtree. That is why this is xn is equal to 1 plus maximum of xk minus 1 comma xn minus k. So, here you will be having xk minus 1 and xn minus k, where k is the rank of the root node. And yn is equal to previously we have seen 2 to the power of xn, yn is equal to 2 to the power of xn, that is equal to here 2 into maximum of, here xn is 1 plus, right. So, here 2 to the power of xn we are writing it as 2 into max of yk minus 1 comma y of yn minus k. So, now there is a function, probability function, which is znk is equal to 1 if the root has a rank k, otherwise 0. So, now this I am going to represent p of znk is equal to 1 and that probability is represented as 1 by n for n elements. Now E of expectation, E of Zn k is equal to 1 by n. So from this probability I am writing the expectation also. So expectation of Zn k is equal to 1 by n. Now initially you have already represented your Yn. Yn is the expected height. That is nothing but expectation height of rbbst. So Yn is equal to summation k is equal to 1 to n Zn of xn. That xn is nothing but 2 max of here 2 into max of yk minus 1 comma yn minus k. Now E of yn is equal to, here if I am taking this 2 to previous, okay, 2 to the leftmost side, then if I am applying summation to the remaining equation, summation k is equal to 1 to n expectation of remaining. So which will be equivalent to, now again this will be equivalent to 2 by n. Why? Because this Zn k is equal to 1 by n. So I am substituting this Zn k is equal to 1 by n in this equation. I will be getting 2 by n, and finally summation of I is equal to 1 to n E of yk minus 1 plus yn minus k, and which will be equal to, now which is equal to 4 by n. Why it is 4 by n? Again here I am taking from k is equal to 1 to n previously, now I am including 0 to n minus 1. That is I am taking out the root now, okay, root now. So if I am taking the root, so it will be equal to 2 into 2 by n, which is equal to 4 by n. So 4 by n into summation of k is equal to 0 to n minus 1 E of yk. And again if I am substituting this E of yk value as ck cube. Why it is summation of ck cube? Because here we have used the induction hypothesis. Okay, now we will not discuss that, but according to the induction hypothesis, that will be equal to, that will be less than or equal to Cn cube. So now again I am writing all these things. So finally which is equal to 4 by n into summation of k is equal to 0 to n minus 1 ck cube, right. So now if I am applying this summation, so here I am representing this summation into integral, that is this summation can be written integrally, which is integral 0 to n x cube dx. So now if I am applying the integral formula, which is some integral of x to the power of n is x to the power of n plus 1 by n plus 1. So which is n to the power of 4 by 4. So here n and n gets cancelled. So here I will be having Cn cube. So as previously I said, the Yn is the expected height of rbbst. So that expected height of rbbst I am going to showcase it as big O of n cube. So Cn cube can be written as big O of n cube. So E of yn is equal to big O of n cube. So finally I can say that if it is big O of n cube means which is equal to big O of log n. So finally E of xn. So expected height of rbbst, that is a randomly built binary search tree, is equal to big O of log n. This is how we have proved it. Now there are okay, whatever may be the tree, there will be some drawbacks also, right. So the first drawback is here the average height of binary search tree. So here average height of binary search tree when both insertion and deletions are used to create it. So here whenever we are using, okay, once we have created our binary search tree, so in middle if I want to delete something, so again I have to start from the starting onwards. Okay, I have to start the process from starting onwards. Why? Because here we are using a randomizer, right. So again my list gets changed, again my random list gets changed. So once the random generated sequence gets changed means again the process has to be applied again and again. So it will take a lot of time to insert the elements in a to insert the elements for already constructed tree. Whereas if I am going with an empty tree, then it is very easy for us. Now to permute the sequence, that is to apply the number of permutations, we should have the sequence in the first place. We should have the sequence in the first place. If we want to insert them as it comes, okay, and we don't know how many items are there in total. That is, for example, in the middle, if I have deleted some more items, so now some more elements. So at that time, if I want to permute again means again I have to read the correct list again and again. Otherwise, the data will be aberrant. There are these two drawbacks occurred in your randomly built binary search trees. Even these drawbacks can also be overcome if you are using a data structure called treep data structure. So this treep data structure will solve all these problems. Okay, if anyone wants, you can go with this treep data structure. Today we have seen what is meant by randomly built binary search trees. So which is nothing but here there is a given list of n elements are given to you. So for those n elements we have to apply the random permutation. So for that random permutation list we have to create the or construct the binary search tree, and after that we have to find out the in-order traversal. That in-order traversal is nothing but your sorted list, and we have seen example also, and also we have seen the analysis. So coming to the analysis, we have seen the height of RBST as big O of log n. So thank you.